Hello, YouTube. My name is Howie Oosterhuis. I'm an assistant professor at the Radboud University in Nijmegen, the Netherlands. And this is a presentation about Doubly-Robust estimation for position-biased clicks. To be more specific, this is a talk based on a TOIS paper, a paper in the TOIS journal, Transactions on Information Systems, titled Doubly-Robust estimation for correcting position bias in click feedback for unbiased learning to rank. This paper, it's the PDF along with the code used for the paper, the slides, this presentation, and this video recording are all available on my website. You can follow the QR code that's on screen right now. I'll also put a link in the description that you can follow. It's quite a lengthy paper. It's 33 pages. For all the technical details, I would refer to that work, but I'm going to do my best here to give you an explanation of that in video format. What I'll do is similar to the paper, I'll follow a two-part structure. I'll start by explaining general counterfactual estimation and the three, in my opinion, most important families of methods in that area. And then I'll talk about counterfactual learning to rank. And the reason I do this is I want to emphasize that there was an existing mismatch between these areas, mainly that we were missing Doubly-Robust estimation in counterfactual learning to rank. Then in the second part, I'll introduce the novel contribution of this paper, which is a way to apply Doubly-Robust estimation to position bias in ranking settings. So let's get started. I'm going to start with the most simple setting that you can think of, which is single item recommendation. So we have a couple of time steps. At each step, we recommend a single item to the user. And the goal is to maximize the total number of user interactions with that item. So you can think of an interaction here as a click. I'll use clicks. It can also be a click followed by a purchase or a click followed by someone watching a video. Whatever interactions make sense for the setting you're thinking of. But I'll just stick to clicks to keep things simple here. The data that we have available here is interaction data logged using a production system policy. With production system, I mean there is some system already running, people are interacting with it, and we observe their interactions in that data set. So the real question here becomes, how can I evaluate a new policy, so a new system, a new thing that I have not deployed yet, based on the data gathered by another system, by the production system. So I want to know how good is a new ranking system based on a previous ranking system. I say ranking system, it's not really a ranking system. Recommendation system is a better word here because we're just showing one item. Now, a very naive thing to do here would be to say, well, if I see a user interacted with an item, and if the new policy is likely to also recommend that item, then that's a good thing, because that's an item which people interact with, and my policy is going to show that item more. So if I visualize that, let's see, on the left I have my interaction data, somebody interacted with item B, I'll just link that with the probability that my new policy gives to recommending item B in the same context. That's what this visualizes. So that's the probability distribution on the right. This is very straightforward, but I call it naive. And the reason is because this approach ignores where the data comes from. It ignores the fact that there was a production system which has its own policy, what we call the logging policy, which decided to show this item, in this case item B, to the user. So the item recommendations that we see in the data set, they're not uniformly random, they're based on the logging policy. And if we ignore that procedure by which data is being generated, we in our evaluation, we let it affect it basically. So we shouldn't ignore where the data comes from when we're doing evaluation. In this example here, you see that item B is very likely to be recommended under the logging policy. So it's going to be overrepresented in our logging policy data. And this happens to be an item that the new policy doesn't recommend very often, but because it's overrepresented, it's going to be punished a lot for not recommending that item or not giving a high probability for that item. Let's put that in formal terms. What I want to estimate is the expected reward. And the reward here is a click signal, basically, right? So I'm going to write that down as R pi, where pi is my recommendation policy. And then it's an expectation over the context. So X is a contextual feature, could be, I don't know, the user or the time of day, whatever contextual features are relevant. Then we're going to sum over every possible action A, that's an item here being recommended. Then we have the probability of the item recommendation under the new policy, the policy I'm evaluating, multiplied with the probability of an interaction with the item. This is just to say, what we get here is how many interactions do I expect if I were to deploy this policy, right? It's the expected number of, the expected ratio of clicks, you could say, the expected click-through rate. A very naive thing to do would be to say, well, I don't know what this click probability is, right? That's what I'm trying to learn. But I have observations, so I could just take sort of the average of that as my expectation, right? So I could just replace the click probability with the observed interaction. So I'm going to estimate the click-through rate by taking an average over all my data points for each observed interaction that I see. I see how likely is it to be recommended by the new policy, and I multiply that by whether it got an interaction or not. These formulas look very similar, but if you actually compute the expected value, we can see there's a problem of bias. So bias here refers to statistical bias, meaning the expected value of our estimator is not the value that we want to estimate. So there's a systematic error, basically. What we see in the expectation is that the logging policy probability enters the equation. Why is this the case? Well, the items here, whatever item A is, right? The item that was recommended at time step I when I was logging the data, that was decided by the logging policy. So the logging policy has decided what this is going to be, and that's why we have this probability of the logging policy here. We're again taking the sum over all actions, and then we're saying what's the probability that the logging policy would have shown this item. So it's now an expectation of what was most likely item that would be shown. This is a problem, right? Because it means that the expected value of my estimate is going to be incorrect, and it's going to be affected by the logging policy. So we have a form of bias here. And you can think of this as selection bias. So basically, we don't observe all actions. The ones that we observe were decided by the logging policy. Now, counterfactual estimation is all about correcting for this kind of bias. The word counterfactual here refers to, I want to estimate what would have happened if I deployed a different policy, so something I didn't do, counterfactual in that sense. And I'll talk about 3 methods that deal with selection bias specifically that are applicable to this scenario. The first one is inverse propensity scoring. Now, the idea of inverse propensity scoring is that we can see this logging policy that selects what action to take as sort of a filter, as something that decides what we will observe, what we won't observe. And what we can actually do is by weighting observations, we can pretend like they happen more or less frequency. Another way to put this, the logging policy is going to over or underrepresent certain actions, in this case item recommendations, based on how likely it is to give each recommendation. But by giving a weight to an observation, we can also make it over or underrepresent, be over or underrepresented, so we can counteract these two. They can cancel each other out. What we do is we take the inverse propensities, which is 1 divided by the probabilities of the logging policy. So in this case, you see that if B is a very large probability, it turns into a very small weight, whereas C here is a very small probability that turns into a very large inverse propensity weight, because it's 1 divided by that probability. If we now take the observation, give it a weight according to the inverse propensity, and then link it to our new policy probability, these two are going to cancel each other out. The reason is if you multiply a propensity with an inverse propensity, you get 1. You get a uniform distribution, Nothing is over or underrepresented anymore. So this is the idea of inverse propensity scoring. Let me put that formally. The IPS estimator, or IPS stands for inverse propensity scoring, still takes the average over all observed clicks, but now instead of just taking the probability of the new policy and multiplying that with the click, we also divide by the probability of the logging policy. So we're working with the ratio between the two recommended policies. So this basically says how much more likely is my new policy to recommend this item than my old policy, and that's basically a weight that we now give to each observation. What happens when I compute the expected probability here is that this division by this propensity is going to cancel out the logging policy probability entering the equation. If you remember from 2 slides ago, when I take the naive estimator, I had this probability enter the expectation, but now we've already got rid of that by dividing by it here. So we have an unbiased estimate. If you compute the expectation, you get the relevance that you want, which is great because that means that we don't have a systematic error here, right? We have an estimate of our relevance. The downside of this, we've solved the bias problem. The downside is that this can have very high variance, especially when propensities are small. Propensities are small, this weight becomes very large, right? If this probability is a very small number, we have an enormous weight, and an enormous weight basically means that one observation here gets very overrepresented, meaning the noise in that observation also gets overrepresented, which leads to variance. So we've solved the bias problem, but we usually have a variance problem because of that. Another way of doing this, which is the opposite end of this, which completely solves the variance problem but still has a bias problem, is the direct method. Now, the idea in the direct method is that we have regression predictions. So I have some model that can predict the click-through rate for each item, and what it's going to do is it's going to take the features of the item or do something else, and it can give me a prediction without needing any observations from the user. So I'm going to represent this by a magic wand. We just have a model or a system, and given an item, it can just predict the click-through rate. So I can apply this to all of the items. So I don't have selection bias because I now have a value for every item. And then I can just link those to the new policy. So I've solved the selection problem. We also don't have variance from our interactions because we're not using the interactions. But as you can see, this doesn't look like a good idea because I'm now completely relying on my regression model. That's why I represent it as a magic wand. I'm sort of trusting that it does its job perfectly. Otherwise, I have a problem because these values here, these clicks that you see, aren't real clicks. They're predictions of click-through rates. In practice, that means that this is almost certainly biased. Let me show that to you formally. So the direct estimator still is an average over our interactions, but instead of using the interaction, we only use the context. Then in that context, we looked at every possible action we could take, so every possible recommendation in our case, and we have a predicted interaction probability. So here's the probability of a click. I've put a hat on the probability here, indicating it's not a real probability, but a prediction. And now, yeah, it makes a prediction for every action, right? So we've very similar to that expected reward that we wanted, we now have this predicted interaction probability. You can clearly see that this is going to be unbiased if my predictions are correct. If I have a model that can correctly predict all the click probabilities, we are going to have the right value in expectation. That's great, but that practically means that I already solved the problem. If I already have a model that can predict all the click-through rates, there's nothing left to be solved. So you can almost be certain that you are never in this situation, right? I don't think you would ever find yourself in a situation where you've already solved the problem that you're tackling with some regression model. So you can expect there to be bias, but there's no variance. We don't have any variance from the interactions. They're completely ignored. So we're now on the other end. We've solved the variance problem, but we still have the bias problem. The idea of Doubly-Robust estimation is to combine these two approaches and to get the best of both worlds. no bias, and very little variance. The trick here is that we're going to use inverse propensity scoring to unbiasedly estimate the error of our direct method. And we can use this unbiased estimate to then get rid of the bias. I'll show you that part. I'll show you how we estimate the error. So this doesn't show the full doubly-robust estimation, but here we are again, right? I'm still going to use inverse propensity scoring. So I still have my inverse propensities, just as with IPS. But now instead of linking it to the observed interaction, I'm going to look at the difference between what did I predict, what's my predicted click probability, and did I see a click or not. So this difference is big if I have a high predicted click probability, but I don't see a click, or vice versa, if I predicted there to be no click and there was a click, right? So this tells us how wrong was the regression, and then we link that to the new policy. So we look at how long are our regressions. We bear in mind, like we correct for the fact that our data is still biased by the logging policy in what errors we observe, and then we can link it to the new policy. To put that formally, right, the doubly-robust estimator, it starts with the direct method. So it starts with the equation I showed you 2 slides ago, where we use our predicted click probabilities to predict the performance of the policy. Then we apply IPS, but instead of taking the click probabilities, predicted click probabilities, or the observed clicks directly, we look at the difference between them. So we look at, did we observe a click, and what was the probability that we gave to a click occurring? If that difference is large, then my model is very wrong and is making an error in a certain direction. If it's the other way around, it can make the error in the other direction. If it's very correct, these values should match, right? So this tells us how wrong is the regression model. I'm still doing IPS here because the clicks that I observe are still affected by the selection bias of the logging policy. Something that I also want to point out is you can write this down as the direct method plus IPS, plus the IPS estimator, minus a covariance estimate. And this isn't very useful in general, so I don't think a lot of people describe it like this, but it's going to be useful specifically for the learning to rank case. So I'm going to bring it up later, but I wanted to point that out now. So what are the properties of the doubly-robust estimator? The reason it's called doubly-robust is because it's easier to be unbiased than for the other estimators. It requires, for each item, one of two things. Both is also fine. Either the inverse propensity is correct, so this ratio here, there might be cases where you don't know that ratio exactly, you have to guess it or estimate it, or the regression estimates are correct. So the direct method, not the direct method, but this predicted click probability here is correct. So for each item, one of the two has to be correct. It's per item basis, right? So for one item, the propensity can be correct, and for the other one, the regression can be correct. Doesn't matter. But in that case, it's easier to be unbiased because it's unbiased whenever the direct method is unbiased. It's unbiased when IPS is unbiased. And then there are more cases where this is going to be unbiased where the others aren't. That's why it's called doubly robust. Another nice feature is it can decrease variance. If you write out the variance using this equation down here, you can see it's the variance of IPS plus the variance of the covariate minus the covariance, twice the covariance between them. So if there's a high covariance, you can actually get less variance than with IPS. I should say in this variance, I'm only considering the item recommendation and whether it was a click or not. I'm ignoring the context just to keep it easy, but we don't need to do that for this. Anyway, we see here how it combines sort of the two properties of the other estimators. So to sort of repeat the 3 main families of counterfactual estimation, we have inverse propensity scoring, where we give weight to observations according to the logging policy probability. This is unbiased if the propensities that determine those weights are correct, but we can expect high variance, especially due to low propensity actions. Then we have the direct method. This is where we purely use regression to make estimates. This is going to be biased unless regression is 100% accurate. which you can assume is never the case. You can assume you're always biased. But you have extremely low variance because we're ignoring interactions. The Doubly-Robust estimator starts with the direct estimator and then uses IPS estimator to correct for it. It has easier unbiased criteria. It's easier to be unbiased in this setting. And it has lower variance than the inverse propensity scoring if regression is somewhat decent. So if your regression is somewhat accurate, you can expect to have lower variance. If your regression is completely wrong, then maybe not, but that's generally not the case. So this gives us an overview, and we can clearly see that most of the time, like the Doubly-Robust estimator seems to have the nicest properties. The thing is, when I started working on this paper, so we're talking in 2022, in Unbiased Learning to Rank, almost all of the work in Counterfactual Learning to Rank was based on inverse propensity scoring. There are some methods that were applying the direct method, but they didn't realize that they were doing it. Things like two-tower models, I would argue, are very similar to the direct method or other forms of click modeling. And we certainly didn't have Doubly-Robust estimation. No one had even tried to apply this. We didn't have any way of getting Doubly-Robust estimation in this setting. So there was a gap between what we saw in the general counterfactual estimation case and in the learning to rank case. And that's the gap that I feel bridged with this work. All right, let's get into that. So I'll start by introducing counterfactual learning to rank and then talk about how we can apply these methods in that setting. To be clear, I'm talking about a ranking setting, a ranking system. The main characteristic for that, what makes it a ranking system, is that we're going to show a list of items. We're not recommending a single item. We're showing a list of items. People can interact with one or more of those items that we show to them. So we might get one or more interactions from a user at each time step. And our goal is to maximize the total number of interactions. Ranking systems are the basis for every search engine, right? If you're looking for something, we're using a search engine. There's a system here that decides what list of items to show you. It's also extremely common in recommendation systems. So many recommendation systems don't just show you a single item, but a list of items which you can interact with. Okay, the first thing that we run into is the number of actions that we have is enormous because ranking is really a combinatorial problem. If we treat each ranking as an individual action, the number of actions grows at a colossal rate, right? This is a problem because propensities have to be spread out over those rankings. I have a visualization here. I don't think it's enough to grasp how big of a problem this is, but you'll see what I mean. So this is the number of top 5 rankings. How many top 5 rankings can we make, given how many candidate items do we have? So if I have 10 items, how many top 5s can I make? Well, it's already about 10,000, right? That's a large number. But it grows exponentially. If we want to have 1 million possible top 5 rankings, we already have it with 20 items, right? If we want 100 million, we only need 42 items. Usually, the number of items that there are in the order of thousands, hundreds of thousands, or millions. So you can see that the number of possible rankings, it just explodes. This means that propensities become extremely small because all the propensities have to sum up to 1. We now have to we have more than millions or billions of actions, and all the propensities should add up to 1. We know that at least one of them will be 1 in a billion or smaller than 1 in a billion. If you remember, tiny propensities cause use variance problems. This basically makes the standard approach not applicable. We can't take each ranking to be an individual action because the propensities just become too small to do anything useful there. So we have this huge variance problem if we just treat ranking the same way as we would any other action. The solution to this that's been proposed is instead of thinking of each ranking as an action, we can also look at the position bias that we see happening with clicks inside of rankings, and then apply IPS on that level. Let me start by explaining position bias. So position bias is the very well-known phenomena that users don't look at the entire list if you show them a ranking, but mainly look at the top. So here is an eye tracking study. All these people were looking at the same page, looking for San Jose parking. And what we see is in these dark blobs here is that almost everyone looked at the top two results. So almost everyone looked here. And then we see there's kind of this F shape or triangle shape. Fewer and fewer people make it down the list. Here at the bottom, at result number 8, less than 50% of people make it that far down the list. So if we now think about where people are going to click, we know that regardless of what we're going to show, people are going to click way more at the top of the ranking than at the bottom, because they don't look here, right? It's not that people didn't like this item. A lot of people didn't even know what there was being shown because their eyes didn't even make it to that part of the page. So you can see this is an unfair advantage for the item down there. What it means for us is that position has a really large effect on what clicks we see. And this is a bias. This is something that doesn't go away if you gather more data. It's not noise. It's a systematic bias. So I can expect my click-through rate just to be lower if I show something at the bottom of the page than at the top. And it has nothing to do with how relevant the item is, whether people like the item, or sort of the things that we care about, right? So we're mainly measuring, if we're looking at click-through rates, how things are being displayed, not how good the items are for the query. To deal with position bias, the high-level approach here is to model the relationship between clicks and quality, or relevance, it's also sometimes called, with a mathematical formula that we can then later invert to derive an unbiased estimator from this model. So for this work, I used the following equation, as you can see here on screen. The probability of a click is based on the item D, the position K, and then specifically on the right we have the probability of R, which usually stands for relevance, but now you can think of it as the quality of the item D. And then the bias parameters are these alpha and beta values that depend on K. So for each K we have a different value. I'll start with the beta parameter. Beta is basically the base click-through rate. So users trust search engines. So there's a percentage of users that will always click regardless of what you show, but they'll always click at a certain rank. And these are captured by the beta parameter here. The alpha parameter captures the correlation between quality and click probability. So being more relevant, how many more clicks did that get you? That's captured by alpha. And both of these can capture the position bias that I showed at the previous slide, because they can vary the amounts for each rank. So we can indicate that at certain ranks, for instance, if no one is looking, alpha and beta are going to be very small. There's a very small correlation then between quality and click-through rate. Importantly for us, and a property we'll use later, is you can invert this formula, right? If I wanted to know probability of relevance and I had the probability of a click and I had the beta and alpha parameters, I could subtract beta and then divide by alpha, and I would have my probability of relevance again. Another way to think about this in this model is we're treating position bias kind of like a filter. If we ignore the beta parameter, if we set the beta parameter 0, you basically have, at every rank, the amount of people that look at an item. So we'll call this exposure, and that's going to act as a filter. So at the top, everyone is looking at the item. So the amount of people that will click is going to represent the amount of people that are interested in the item, how good the item is. If we go further down the list, for instance, here we have 50%. If there's a place where 50% of people we look at an item and then decide to click or not, we can multiply their click-through rate times 2 and to get sort of the original click-through rate back, right? So that's what this weighting is going to, it's what we're going to do with our inverse exposure weights. Similarly, for 40%, it's 2.5. So it's the same idea as inverse propensity scoring, but now instead of basically how likely the recommendation is, the ranking is, we look at how likely is it that people looked at an item in our ranking. So our propensities are based on exposure, not on the probability of the entire ranking, right? This is great because these exposure propensities are much smaller than the ones that I showed you before, right? We're not talking 1 in a billion here. We are still in the 1 in a 10 or 1 in a hundreds range, basically. The model I'm going to use specifically is based on expected correlation. That's what I call exposure. So I'm going to introduce a propensity, which is the expected alpha value of a document. So basically, how likely the expectation over the rank at which this item might be shown and the alpha at that rank. So I'm summing over all ranks. How likely was the logging policy to show an item at this rank? And what's the correlation between click probability and quality at this rank, or relevance probability? So this is just the expected alpha value for a document or an item. And then I can use my IPS estimator with trust bias corrections in the following form. So this is specifically for position bias. So again, we average over n observations. For each click, I subtract the trust bias correction at the rank at which this click took place. And then I divide by my propensity, which is the expected alpha value here. It's the same idea as inverse propensity scoring. We're reweighting to correct for over or under exposure, but we are avoiding extremely low propensities. So the rho values here are not going to be 1 in a billion. Again, they're going to be 1 in a 100 or 1 in 1,000 on that sort of scale, which is still not always ideal, but it's much better and it keeps things feasible. Whereas the direct approach of just treating the probability, using the probability of rankings, is not feasible at all. Another additional condition that we have here is I now need to know these alpha and beta parameters. So it's a bit more difficult because we need to estimate alpha and beta as well. There are many methods that do this, usually through randomization or applying a click model. I'm not going to go into those. That's not what this paper is about. But I have other presentations if you're interested in that. You can see them on my channel. I'm assuming that we know alpha and beta, but we'll also consider the case where they're wrong. Okay, now we've seen the inverse propensity scoring for position bias. Basically, what I've shown you on this slide, it's not very novel. This already existed, so at the time of doing research, this was sort of the background. The question is now, how can we apply Doubly-Robust estimation in the same way? So the question I had when I started this research is, why is there no exposure-based Doubly-Robust estimation for learning to rank yet? Why do we only have inverse propensity scoring? The first thing to note is that the direct method needs regression of this R, right? This relevance or quality parameter. And standard Doubly-Robust estimation also needs to know the difference between our estimate and our regression estimate and what we observed. So that would be the difference between the predicted relevance and the true relevance. The obvious problem here is that we never see that. We don't observe the relevance or quality directly ever, right? We only have samples from clicks. So we observe clicks. We never observe relevance. So we never observe our error in relevance estimation. So we directly, at least. We can never say this is how wrong our relevance estimation was exactly, because we never observe it directly. This is why I think the field hadn't moved beyond inverse propensity scoring, because it doesn't seem applicable because we don't observe our errors directly. Okay, I'll start by mentioning how I think the direct method can be applied, and then I'll go into to the Doubly-Robust method, because we need the direct method for the Doubly-Robust method, if you remember, right? It starts with the direct method plus IPS minus this covariate. There are many ways that you can get a regression model to give you relevance estimates. A lot of click models do this. For this paper, I introduced a new cross-entropy loss, and if you remember, cross entropy loss is the real probability times the log probability of an event happening. And then that's something you take the minus and you minimize it. So I built upon previous work that did this and made a small improvement here. So we have our IPS estimator here. We take the difference between the observed click and the click probability if an item is completely not relevant, multiply that with our prediction of a log probability of it being relevant. So this is our probability of it being relevant. So what we look at here, what we have here is the difference between the click that we observed and the click probability if the relevance was 0, which is then you just have beta left, right? So how many more clicks did we observe than we would predict if relevance was 0, and that's being multiplied by the inverse propensity weight, which then gives us a IPS estimator again, right? So basically here we just have the IPS estimator. On the right, we have something that looks like previous work put 1 minus the estimator here to predict the probability of something not being relevant. But I didn't like that 1 in there because then regardless of what you observe, you always have this 1. So I replaced it with an alpha. I'll show you in a second how I can do that. But now we actually have the difference between the observed click and the click probability if an item was completely relevant. So there's an interesting symmetry here that we'll see more of later. And then we multiply it with 1 minus the predicted probability, so the probability of not being relevant. So here we have an IPS estimator, as I've shown you before. Here it's actually an IPS estimator of the opposite of it being not relevant. You can think of it as like 1 minus the probability of being relevant that's being estimated there. The novelty here comes from the second weight. And basically what my observation is that, well, this here is just the minus of the inverse propensity scoring estimator. So that expected values is the probability of relevance. And then we're left with alpha divided by this propensity. The propensity was the expected value of alpha. So this is just 1. So we just get 1 minus probability of relevance. But the nice property is that instead of putting the 1 in here, it's alpha, which means if an item is not being shown, the alpha is also close to 0. Or if it's shown in a position where it gets very little attention, that means that we don't have like a standard weight against a relevance estimate. Either way, this enables unbiased regression of relevancy. So we can use this loss to optimize a model that gives us predicts estimation of relevance given features of a document. The insight is now we have a direct method, we have our IPS method. All that we miss for a Doubly-Robust estimate is the covariance, right? There's a covariate that we subtract. We don't have that yet. So the next step was basically what should this covariate be? And we know from general counterfactual estimation is that it should have the same expected value as the direct method and a high covariance with IPS to get the properties that we want. Using these requirements, I figured out that this is the best covariate estimator that I could find actually, which let me explain what's going on. It's again, we're taking an average. This is now we are looking at the ratio between the propensity and the observed alpha at that observation. So when an item was being shown, multiplied by the direct method estimate. This is an unbiased estimate of the direct method estimator. Again, because this propensity is just the expected alpha, so this turns into 1, and then we are left with the direct method prediction. So it will cancel out the direct method. But it's very weird. When I first found this, I didn't quite know what I was looking at. It wasn't until I took this estimator and this covariate estimate and then plugged it into the direct method estimator when I saw the full equation and I understood what was going on. This is that equation. So this is our novel Doubly-Robust estimator for position bias, the first of its kind to the best of my knowledge. Let me walk you through it. We start with the direct method, right? Our regression-based estimates. Then we we have our IPS estimator based on exposure propensities. And inside the IPS estimator, we're using the difference between the click that we observed and the predicted click probability. So based on our regression model, what is the click probability at that rank? And it's subtracted from the click that we observed. So the way that I think about this is we look at the difference between how many clicks do we see versus how many clicks do we expect to see based on our relevance prediction. How many more or less clicks do we see? And then we use our exposure weight to go back to what that means in differences in relevancy. So if we're at a position where there's a very low correlation between relevance and quality, a small difference should be bigger, right? A small difference in clicks is a bigger difference in relevancy. Vice versa, if we're at a place where there's a high correlation, then they should be about the same. So we're looking at the difference in clicks and translating that back to a difference in relevancy. This is unbiased when we still need alpha and beta to be accurate. So we still have that requirement, same as for exposure-based IPS. But for each item, we either need to know the logging policy propensity, so what did our logging policy do exactly, or our regression estimate should be correct, this thing over here. Again, it's an or statement for each item. So it's going to be unbiased when the exposure-based IPS estimator is unbiased and when an exposure-based direct method is unbiased. But also in cases where neither are biased. So it's doubly robust in that sense. To the best of my knowledge, this is the first Doubly-Robust estimator that does not require directly observed errors. This was the main problem to solve. We don't see the errors directly. We infer them from clicks and then translate them to what they mean in terms of relevancy or quality. Okay, so this is our main contribution, or my main contribution, I should say. So another thing I can prove here, which is very nice, is that if our regression estimates are in the range between 0 and twice the true relevance value, then we can prove that the Doubly-Robust estimator has less or equal bias and variance than IPS. I'm not saying it's only the case when that's the scenario. That's not what I'm saying. I'm saying we can prove in this scenario for sure that it's better. We can also improve in other areas, but mathematically I can't prove that. We can look at it experimentally, which we'll do in a moment. But there are definitely scenarios where we can prove that this is the case. There's some caveat. The Doubly-Robust estimator turns into an IPS estimator again when all the propensities are always equal to the alphas. This doesn't happen if you have a stochastic logging policy, if there's randomness in your logging policy, or if you're doing propensity clipping, which I think almost everyone does, so I don't see this as a big problem. All right, that was the mathematical explanation. I want to give you some intuition on why this works so well. When you do inverse propensity scoring, and let's say there is a query for which you have a ranking and there's documents for that query, but they were never displayed to the user during ranking. So here, only the top 4 are being displayed, everything else is not being displayed. IPS is going to assume that those other documents have 0 relevance, because its default is 0, right? We're reweighting observations. We have no clicks. No clicks can't be reweighted. It stays 0. As a result, IPS can only really re-rank the top items. So if we follow the IPS estimator, if we do exactly what it would like follow it to its maximum, it's just going to re-rank the top. So IPS is basically just going to re-rank the items which would show and ignore and leave the items at the bottom of the ranking the same way if they were never displayed during logging. Any item that you never displayed will move to the bottom of the ranking. For the direct method, we don't have this. The direct method can freely move around everything because it can just make a prediction of everything. So any item here can be placed anywhere else. There's no difference between what was displayed during logging and what wasn't displayed during logging. But it's not following any of the clicks. What Doubly-Robust estimation does, you can think of it as we first re-rank the items according to our regression estimates. And then we use the clicks to sort of correct those estimates again. So now everything can move around the ranking. If there's an item that wasn't displayed, it can still make it higher to the top of the ranking. But we're still using clicks when it's possible, right? We're still using clicks when it's there. But we might have items up in the ranking that were never displayed. I think this helps reduce variance quite a lot because it means the logging policy has less control over the final ranking. In the IPS case, the logging policy can basically decide these items, I'm not going to show them, so they're going to make it to the top of the final ranking when we try to learn from that data. And Doubly-Robust estimation corrects for this in a large way. It at least makes it so that that decision isn't fully being made during the log. But again, an intuitive way of thinking what we're doing is we start by our regression model. How does it think we should rank everything? And then we use the IPS model or estimator to correct that ranking. And we can use that during optimization to learn the best ranking. Let me show you the results some experimental results before I conclude this presentation. What I've done is I've done simulations based on commercial search engine data sets. In these simulations, we know the relevance judgments because they're in those data sets. These are expertly judged documents. We simulate clicks based on those labels with position bias and noise added. This is nice because it means I know the ground truth, and therefore I can properly investigate what's happening. Position bias parameters are based on previous empirical work, so we are somewhat confident that they are in a realistic range. I tested a top 5 setting and a full ranking setting with estimated and known biases. So settings where we know the bias and settings where we had to estimate the bias. I'll start with a top 5 setting, so only 5 items are being shown. Bias is estimated from the data. We don't know bias beforehand, like in a realistic setting. And this is what the results look like, right? So the metric here is the expected number of clicks under the new ranking policy. So the higher, the better. Expected clicks on relevant items, by the way. So clicks where users are actually happy with what they clicked on. And the x-axis is the number of queries in the data set. So this ranges from a data set with 100 clicks to a data set with 1 billion clicks. And all of these results are based on, I think, 50 repetitions of the simulation. This is not an online experiment. It's not that we add more data to our data sets. We just simulate different amounts of data to look at the effect of the performance. This line down here is the logging policy. So this is a production system. This is the performance it has. The line up here is a model trained on the ground truth. So this gives us an upper bound, sort of what we can expect on what performance is possible in this data set. This pink line is the naive approach. If we ignore the effective bias altogether, we can improve on the production system, but not by much, right? This is very typical for learning from biased data. You converge at the wrong place, and we're stuck there because we're converging in bias loss, and the minima of that bias loss is not the minima of a true loss or the optimal metric value. Then let's look at inverse propensity scoring. It's this green line. You can see it also improves over the logging policy, but it doesn't reach optimal performance after 1 billion clicks. It doesn't look like it's going to do it anytime soon. We need to multiply by multiple factors of 10 to continue the trend here, right? So because we're on this logarithmic scale. We know the inverse propensity scoring is unbiased here. So the bias is estimated, but at this point, it has so much data that the bias estimate is very accurate. So that's not the problem. It's variance. The variance is preventing it from reaching optimal performance here. Yeah, that's why it's stuck. Then we have this blue line, which is the direct method. I trained the regression model on the same data that's available here, so it doesn't use any additional data. You can see in this setting, it learns much faster than inverse propensity scoring, and it reaches higher performance in the range that we see as a result as well. Finally, we have this red line, which is the Doubly-Robust estimator. It, in many places, significantly outperforms the direct method, so it's an improvement, even though it's very close to what we see here. But it's everywhere. It's pretty much either the best method or tied together with the direct method to be the best method. As I said before, inverse propensity scoring was basically the state of the art for this kind of setting in previous work. So if we sort of look at the performance we reach here and then reach of the performance we reach now at Doubly-Robust estimation, we only need 100,000 interactions or queries instead of 1 billion queries in our data set. So we have an improvement of factor of 1,000. We need 1,000 times less data to reach the same performance. That's an enormous difference. I can't understate how big that is. Most previous work has improvements of a couple of percentages, not factors of 1,000, right? So when I saw these results, I triple checked them because they were unbelievably high. I'm not saying in the real world you will get a similar improvement, but this is a very difficult task to get such an improvement in, and it's likely to also mean that there's a substantial difference in a real world setting, as best as we can tell. Here's a different data set. The previous slide was on the Yahoo data set. This is based on a Bing data set, which is called MSLR Web 30K. We see about the same patterns. Again, if we look at where IPS ends up and how much data we need, its difference is about 1,000. Again, there's a small improvement over Doubly-Robust estimation over the direct method, and then a big improvement over inverse propensity scoring. Then we have the Stella data set. This is based on an Italian search engine. And this one is very interesting because now we see the direct method and inverse propensity scoring have about the same performance, but Doubly-Robust estimation has like substantially better performance. We see that it does much better now than both. So this shows that it's not just doing a maximum operation, it's really combining these two in a meaningful way, in a more robust way that leads to better performance. The performance that these methods reach, again, if we look at when Doubly-Robust estimation reaches that, we have a difference of about 1,000. So that's, yeah, excellent. So these are great results, right? This is really something that we would not expect beforehand to see such like improvements in efficiency. The fact that Doubly-Robust estimation can reach optimal performance within a billion with a billion queries is really much better than the previous methods. I do want to point out that initially we have a period of worse performance. So the same here on the MSLR data set. This is a result of the regression model not being very good when there's very little data. And that could actually make things worse. So if you have a bad regression model, Doubly-Robust estimation could actually get worse than IPS. I don't think this is a very big issue because it only happens when there's very few data. We also have follow-up work that in the area of safe unbiased learning to rank that prevents these kind of things from happening. I won't go into more detail here, but you can see of some of the papers by Shashank Gupta that actually deal with this issue. Okay, that was the top 5 setting. In the full ranking setting, I tested a scenario where in this case, the bias was known. We've given the exact bias parameters for all ranks. And now things shift, but the Doubly-Robust method is still the best overall, right? So in this case, we see the direct method actually doesn't reach optimal performance. It's likely that it's harder to deal with. I don't think it works very well when there are positions with very low exposure, very low propensities, which there are a lot more in the full ranking setting, right? You have a lot of positions where these propensities are very low. It can't deal with that very well. That's why I think it doesn't converge or doesn't reach optimal performance here yet. Inverse propensity scoring needs more time to start, right? It needs more data to start really improving over the production system, but then it reaches optimal performance at convergence. So it's doing better at the end, whereas the direct method is doing better here at the start. The robust method does both, right? It seems to provide an improvement over the direct method everywhere, although the differences are smaller. But really here it has this sort of good start of the direct method and the excellent convergence of the inverse propensity scoring method. So it's again the best of both worlds, as we hoped when we were designing this method. So that's excellent. On MSLR, it's different. Here the direct method does it do well. Again, the Doubly-Robust method gives you the best of both worlds. Same on the Stella data set. Really, the takeaway here is if you don't know which method is going to be better, it doesn't really matter, right? Whether inverse propensity scoring or the direct method is better, if you apply Doubly-Robust estimation, you'll most likely have the best of both worlds. Finally, so far I've either estimated the bias or I've given methods the bias parameters. And the estimation either found approximately the right values or, well, when I give them, of course, they're accurate. But in reality, you might end up with incorrect bias estimates for whatever reason. And I wanted to know what happens to the methods. Are we robust to incorrect bias? So what I did here is I reran these experiments, but now I set the position bias parameters to the most wrong place I could be. I think I swapped the order of it. So it's kind of like assuming people start from the bottom and move up to the top, which is the opposite of what they were actually doing in the simulation. So it's kind of a worst case scenario. What we see here, so these dashed lines are the new performances. We see that all the methods suffer under this, as expected, right? They can't correct for the effective position bias in this case, because or the correcting for the wrong position bias, to be more precise. However, we still see statistically significant improvement of the doubly-robust estimator over these other two estimators. So even in this worst case scenario, you're better off using doubly-robust estimation. Here's the same on the MSLR data set and the same on the Stella data set. So the general conclusion, which is the doubly-robust is your safest choice, your most robust choice, remains true even when the bias parameters are completely incorrectly estimated. Okay, let me conclude. The main takeaway messages that I would like you to have for this presentation is position bias affects interactions with rankings, and this is going to disrupt your evaluation and optimization. So please don't ignore position bias when you're learning from clicks with rankings. The existing solution to this was inverse-propensity scoring based on exposure. As I noted, not on action probabilities, but on exposure probabilities or propensities. And the main contribution of this paper was a doubly-robust estimation method for learning to rank, which means that it uses exposure-based propensities instead of action-based propensities. This is something that we just did not have up until this work, and this work was the first to introduce that, right? If applied correctly, if you have decent regression, you're going to have less bias and less variance than inverse propensity scoring, which can make a huge difference. In our experimental simulations, I saw over 1,000 times data efficiency gains in top 5 settings. Again, these are enormous gains that you rarely see in such simulations, and they are highly indicative of that this would be a good method to try in a real-world setting. The higher level takeaway message is that basically with this work, we now have state-of-the-art counterfactual estimation for counterfactual learning to rank. There's no longer a gap between counterfactual estimation, where we had these from inverse propensity scoring to doubly-robust estimation, to counterfactual learning to rank when we only had inverse propensity scoring. We now have state-of-the-art methods from both fields, from the general field in the learning to rank field. So I think that's very important and could be a very important result on the long term. Thank you for listening to this very long presentation. I hope it helps you in understanding this work better. If you really want to get into the details, or if you're more interested, you can find the paper following the QR code here or the link in the description. The code used for all the experiments is also available. The slides that you looked at are also shared on the website. And yeah, with that, I want to thank you for your attention and for engaging with my work. And yeah, feel free to check out any of my other presentations on my YouTube channel. Thank you, and bye-bye.